starting on page 213, we're only going to do a little bit out of the actual section, okay? Our learning targets are to construct the perpendicular bisector of a segment, which you already know how to do. When we constructed the bisector of a segment, and when we constructed a line perpendicular to another line, we did the same construction. So if the same thing makes bisector and makes perpendicular, it makes a perpendicular bisector. Because guess what a perpendicular bisector is? It's a bisector that's perpendicular. Okay? So we already know how to do that. And then constructing a line parallel to a given line. That one's going to take a little bit of work. Okay? But there are some things in section 3.6 that I want you to know, even though they're not officially part of our standards for this course. Okay? So if you look on page 213, the distance between a point and a line. And we will use this throughout the year. Okay? Our standards now actually expect you to already know this, but I doubt that you do. Okay? The distance between a point and a line, well, the distance between a line and a point not on the line is the length of the segment perpendicular to the line from the point. All right, that sounds kind of complicated. Think of it this way. Here we have a line. Here we have a point not on the line, and we want to measure the distance from that point to that line, or from that line to that point. They mean the same thing. If you had a ruler, let's say that this represents a ruler, would you lay it down like that? That? How would you try to do it? Straight up. You'd try to make your ruler perpendicular to your line, wouldn't you? Because for two reasons. One, that's the shortest distance from the line to the point. And two, that way we ensure, there's only one way to do that, right? So if we all do it that way, we'll all get the same answer. Whereas, whatever that angle is duplicated over here. So there's two different ways to do that if we said, well, always use a 30-degree angle. So you always try to make it perpendicular. All right? So the distance from a point to a line is the length of a segment that's perpendicular to the line from the point. So whatever this length right here is, that's the distance from the point to the line. Okay? So y'all kind of did know that intuitively, didn't you? You figured out that was the best way to do it. All right. Now yesterday we had a day before, whenever we actually had class, we had the parallel postulate. Now we have the perpendicular postulate. If given a line and a point not on the line, then there exists exactly one line through the point that is perpendicular to the given line. And again, intuitively, you knew that when you knew perpendicular was the way to go. There's only one way to do that. And since there's only one way to make it perpendicular, that seems like a good way to measure it, instead of all these other measurements we could come up with. You with me so far? Now, the distance between two parallel lines is the perpendicular distance between one of the lines and any point on the other line. All right, so this is why this is why in this section we're talking about distance. So if I've got two perpendicular lines, two parallel lines, and I want to measure the distance between them. See, we're faced with the same issue. Would I want to lay the ruler down like that to measure the distance? No, I want to try to get it so that it's perpendicular. And since the lines are parallel, if I make that transversal perpendicular to one of the parallel lines, isn't it automatically perpendicular to the other one? Yeah. So you have to have that little segment there that's perpendicular to both of them. And that's the distance between those parallel lines. Not, oh, now what's going on? No, not something like that. That's not a good way to measure distance. So we call that the perpendicular distance. And from now on, we're just going to call it distance, because we all know that distance means perpendicular. Got to be a perpendicular segment to measure the distance. You still with me? All right. Next theorem. In a plane, if two lines are equidistant from a third line, then the two lines are parallel to each other. So, here's what this means. All right, let's look at line A and line B. If we're looking at line A and line B, and we see that the distance from A, well, let's name this one too, C. And let's name it something else. Let's name it M. If we see that the distance from line A to line M is equal to the distance from line B to line M, then that's what equidistant means, equal distance. So the distance from A to M equals the distance from B to M. That means A must be parallel to B. Mm-hmm. Yep, that comes straight from the parallel postulate. Okay? All right, still with me? Because now we're going to get to the things that you're going to do today. This is tough. This is going to be the most difficult thing you've ever done in your life. Turn to page 218. All right, copy each figure. So, quickly, make a little sketch of this figure on your paper. Now, the directions say construct. I'm going to change that to sketch the segment that represents the distance indicated. All right, for number one, the distance indicated is we're supposed to have the distance from point Y to line TS. Okay? What kind of a segment represents distance from a point to a line? A perpendicular segment. So look, if I start at Y, and my job is then to draw a segment that's perpendicular to line TS. None of these work, do they? They're not perpendicular. But TS doesn't stop at S, does it? Now can I draw a segment from Y perpendicular to line TS? And then since we're sketching, it may not exactly look perpendicular. Put a little perpendicular sign, you're done. So that's the hardest thing you've ever done, right? Okay, good. No?
Probably drawing the shape.
It's actually drawing the shape is hard. But the concept of drawing a segment from a point that's perpendicular to a line, not all that tough, right? Well, let's try number 2. So sketch that trapezoid. Well, surely we'll find this one difficult. We need to draw a segment from point C to line AB that represents the distance from C to line AB. It's kind of scary, the level you're operating at now, isn't it? Let's look at number 3. Fortunately, you don't have to draw that. Not sure what that is. It's supposed to be band members. After forming a line, Every even member of a marching band turns to face the home team's end zone and marches 5 paces straight forward. At the same time, every odd member, it's not nice to call them odd members, turns in the opposite direction and marches 5 paces straight forward. Assuming that each band member covers the same distance, what formation should result? All right, so here's what's going on. This guy does that. This guy does that. That, that. So we end up with 2 parallel lines. All right, so they form 2 parallel lines. Ooh, and you know what else would be true about those parallel lines? Yeah, they're each going to be equidistant from the 50-yard line. They're going to be 10 yards apart. Now, how do you want to say all that? Let's just say it. They form 2 parallel lines equidistant from the 50-yard line. They will be 10 yards apart. All right, the justification for our answer would be I don't know how to word that right to make that a justification. Maybe I have already justified it. What's the book say? Yeah, they don't say. I think we're good. I'm not sure that's a justification as much as it is an explanation, but that's the best way I know to explain it. We good with 3? All right. Now, number 8. Find the distance between each pair of parallel lines with the given equations. Now, the book does a lot of these. We're only going to do the simple ones. We're only going to do horizontal lines and vertical lines. So, with horizontal lines, by the way, how do I know these are horizontal lines? Because they don't have an x. It's y equals the y-intercept of each line. It's y equals b. So if I graph y equals 7, 1, 2, 3, 4, 5, 6, 7, and I graph y equals -3, to find the distance between them, I would need a segment perpendicular to them both. And the distance is whatever the length of that segment is. What's the length of that segment? 10. Can you figure out a way to get 10 without actually drawing the graphs? Yeah, the big one minus the little one. All right, 7 minus -3. So distance equals 10. Let me make one up while we're here. What if I made this up? What if I said x equals 4 and x equals 8? What's the distance between those 2 vertical lines? 4, right? Big minus little. If you don't see it, 1, 2, 3, 4, 5, 6, 7, 8. What's the distance of that line segment perpendicular to them both? 4. All right. Okay. Now let's get to the actual learning targets. Construct the perpendicular bisector of a segment. All right, get your compass and protractor out. Yeah. All right, remember how it works. Put your compass point At one end point, stretch the pencil out more than halfway to the other end. Arc above. Arc below. Then you move your point to the other end point. Arc above. Arc below. And now when you connect, that one little segment is perpendicular to the given segment, and it also bisects the given segment. And that's what a perpendicular bisector does. It's perpendicular to a segment, and it bisects the segment. That's how it got its name. So, I'm hoping we're going to be really good at this construction. Okay? Now, the next one's more challenging. I'm going to give you the directions here, and we're going to do one where we construct a line parallel to a given line. And then when we're done, I want you to tell me how come it works. So kind of be thinking along those lines as we do this. All right, so we have to start with a given line. So use your straight edge to make a line on your paper. All right, and what we're going to do, so that's our given line. I'll name it something just so we'll have, that's line M. So we're going to construct a line that's parallel to line M. Use your straight edge again and construct a line that goes through M, and this line is going to be a transversal between line M and then the line that's parallel to it that we're going to construct. Doesn't matter what kind of angle you form there, just, just make one. So has everybody got what I've got? And here's what we do next. We take our compass, we put it at the vertex of the angle that was formed. And we make an arc that goes through both those lines, both sides of that angle. Okay. Now we need a reference point on our transversal. So just somewhere above the little arc you made, make a little point. And now we're going to do the same thing we just did. We're going to put our point of the compass on that point, and we're going to draw an arc. It's got to go through our transversal and then just make it pretty large down here in the interior of our figure. Yep. And the reason we keep the compass the same is compass measures. So don't change your measuring instrument midstream unless you have a reason to. And we're about to have a reason to. Now, I'm going to put my compass point here where my first arc crosses the transversal, and I'm going to measure the distance. Oh, wow, that's a coincidence. Put the compass point where the arc crosses the transversal, put the compass pencil where the arc crosses line M. Mine just turned out not to have to move, but that's coincidence. I didn't mean for that to happen. You with me? Make a little arc right there. So that arc we just made is where the original arc went through line M. So the distance between our compass point and our compass pencil needs to stay the same as we move up here to where our second arc crosses the transversal and then cross that one. Everybody see what I did? Kept it the same. The first two arcs have the same compass setting. The blue arc and the black arc have the same compass setting. The red one and the red one have the same compass setting. All right. Take your straight edge. Make a line from your point through where the arcs intersect. And we have constructed parallel lines. All right, before we practice that one again, can you tell me why that worked?
Mine's like this. Yeah, that's what you need to keep your compass settings the same.
Maybe the compass settings didn't stay the same, or maybe it's just a little bit of human error. If I see all those marks on your quiz, then you'll get it counted right. Okay? All right, so nobody knows how come that construction works? JR?
Because just copy first the angle M, the angle line M has with the transversal into the other line.
Somebody over here was saying corresponding. What we did is we construct, because wasn't that the same construction we did when we copied an angle, when we constructed a pair of congruent angles? It was the same one. It a little different with the transversal. What we did is we constructed a pair of corresponding angles that are congruent to each other. And according to, oh, no, it's from the other lesson. According to the corresponding angles postulate converse, if two lines are cut by a transversal so that corresponding angles are congruent, then the lines are parallel. So we made it so that two lines are cut by a transversal so that corresponding angles are congruent. We constructed that to happen. The conclusion of the postulate is, well, then the lines are parallel. Cool, huh? We actually used geometry to do geometry. Let's try this construction again. What do you say? All right, so let's try this again. Everybody with me, even if you think you got it. Let's start with a line. So I'll call it M again, just to have something to call it. So there's line M. We are going to construct a line that is parallel to line M. We now know what we're trying to do. We now know that we're trying to use the corresponding angles, so maybe that'll help if you know how it works. Let's make our transversal. You can choose wherever you want to make your transversal. Doesn't really matter. Okay? So make your transversal. Now we need our compass. We put the compass point on the vertex of the angle. Just stretch the pencil out however far you want to stretch it out. Whatever is comfortable for you to use. And then you make an arc. through line M and through the transversal. Leave that compass setting. Do not change it. Let's pick a point really at random to make our parallel line go through. So put that other point on the transversal. So we put our compass point on our point, make an arc that goes through the transversal, and make it big enough that the parallel line will go through that arc. We made both arcs with the exact same compass setting. You with me so far? Okay. Now, to guarantee that our corresponding angles are going to be congruent to each other, we put our compass point where the first arc crosses our transversal, and we measure out. I've got to move my pencil just a little bit. I've got to get it so that the point is where the arc crosses the transversal. The pencil is where the arc crosses line M. With me? And we make a little arc. Now, oh, I accidentally moved my point. How did that happen? There, put it back. Now, we put our compass point where the other arc crosses the transversal. Do not change the setting. Once you've measured, don't change. And we make an arc crossing that arc. Now we take our straight edge. We go through the point we put on the transversal and through where our arcs intersect. And we have constructed parallel lines. Work out better this time? All right. Questions? All right, here's your assignment then. On page 218, 1, 2, 3, 8 through 12, 21, 22, 48 through 56, 60 through 65, and practice your constructions.